Hello, everyone. Welcome to the March 26th edition of our online class. Couple reminders, there's no Pearson homework this week, and be sure to submit your notes after each class. All right, so what are we talking about today? Today, we're going to talk about section 4.4. So what is this section about? This section is going to talk about representing representing vectors with a different basis. All right, so let's start with a question, and then we'll go from there. So if I have a basis beta that's equal to this collection of vectors, all right, is a basis for the vector space V, okay, and we have a vector X that is a vector in V. How many solutions are there to the equation C1 times the vector B1 plus Cn times the vector Bn equals X? How many solutions are there? Well, we know these vectors are linearly independent, so there can only be 1 or 0 solutions, and we know the vectors span V, so there must be 1 or more solutions, and that leaves the only possibility, which is 1 solution. So we're going to show today that basically every vector space that is n-dimensional can be thought of as roughly equal to Rn. So let's take a look at the following theorem, which tells us exactly what we just looked at above. And it says, let B equal this collection of vectors. So it's a basis for the vector space V. Then for each vector X in our vector space V, there is a unique set of scalars. In this case, we'll typically use real numbers, C1 up to Cn, such that this is equal to X. And furthermore, we have a special name for these scalars. So in the theorem above, we call these coefficients the coordinates of X relative to beta. So these are basically the coordinates in the basis of beta, or we call it the beta coordinates of X. So these are two phrases that mean the same thing. Basically, these beta coordinates, or the coordinates of X relative to beta, tell us how to write X as a linear combination of the vectors B1 through Bn, which are the bases. And furthermore, we have a way of writing it in something that looks like a vector form. So if I want to write out what this looks like, I write it in this vector form. All right, and we call this expression over here and the expression on the right, the coordinate vector of x relative to beta. Or we might call it the beta coordinate vector of x. So that's what we call this vector that contains those coefficients C1 through Cn. And last but not least, we call the map where we send the vector x to the coordinate vector of x. We call this the coordinate mapping determined by B. The coordinate mapping determined by beta. So what do we notice about this coordinate map? Well, the vector x is in our vector space, but the coordinate vector is actually in the real numbers to the nth power. Okay, so I'm going to have you guys, I'm going to work on an example from the book and show you how this works. Hopefully my device will color this well. Okay, so we're going to look at an example where we have a basis with two elements, B1 and B2, and we're going to let B1 equal the vector 1, 0, and we're going to let B2 equal the vector 1, 2. Okay, so let's look at this coordinate vector for x. We don't know what x is, but let's say it's equal to -2, 3. What is this telling us? This is telling us that x is -2 times b1 plus 3 times b2. This is a way of expressing the vector x in terms of these two basis vectors. And so if we do this little computation, we see that what we get is 1, 6. Okay, so that's the vector x. So this part is the coordinate vector, well, the beta coordinate vector of x, and this part down here is just x. So we're going to create two graphs and show you what's going to happen. So we have our standard graph here. So you can have your standard graph paper. Okay, we'll make that the origin. And let's plot where the vector b1 is. So this is where the vector b1 goes. So if the vector starts at the origin, it will go to that point right there. That's b1. b2 is right here. And let's see. This is e1. That's the standard basis vector. This is e2. And last but not least, we have x, which is all the way up here at 1, 6. 1, 2, 3, 4, 5, 6. So this is x. Okay, so this is essentially our coordinate grid with using the standard basis. So this is our grid using the standard basis. Okay, but that's not the only way to represent the grid. So let's look at a different grid that you might not be as familiar with. So 1, 2, 3, 4, 5. So here we still have the vector b1, and we know that b2 should go somewhere roughly right here. That's roughly where b2 is going to go. So we're going to create a new grid that looks something like the following. So that is the vector b2. And now we create a new grid where we use parallelograms. So they're a little off, but you're going to get the idea. All right. Okay, so we have a new coordinate grid. This is the grid using our basis beta. And what do we find? Well, we see where b1 and b2 are. And so we need to see where x goes. And what we find is x is right about here. And so what do we see? In the old coordinate grid, x was equal to the vector 1, 6, because we went over 1 in the x-axis and we went up 6 along the y-axis. But in our grid using beta on the right, we start at the origin, we go to the left by 2 b1s, and then we go to the upper right by 3 b2s. And we see that this has coordinates -2, 3 in our basis beta. And so you see that these are different ways of describing the exact same plane. On the left, we use the coordinate grid that you know and love. But on the right, we use a new coordinate system that is just as valid. There's only one way to represent each point, but it uses a different way of measuring it. Okay, so now it's time to give you an example. So using the same basis as before, I'm going to let our vector x equal the vector -1, -8. This is using the standard basis. And now I want you to pause the video and see if you can calculate what x beta is. Those are the beta coordinates. So to remind you, this means that you want to solve the equation right here. In other words, you want to solve this equation. All right. Oops, sorry, that's not quite right. I think this is 1, 2. All right, so pause the video and solve for the coordinate vector of x relative to beta, or the beta coordinate vector. All right, now that you've had a chance to solve for it, you probably got that the coordinate vector is 3, -4, because x is equal to 3 times b1 minus 4 times b2. All right. All right, so we see that going from the beta coordinates to the standard basis coordinates, that's pretty easy. Going the other way can be a lot of work. Is there an easier way? And that's what we're going to answer right now. Okay, so let's look, it's a little bit of theory. Let's look at a vector x, and we know that it's equal to some combination, some unique combination of these basis vectors. Okay. So what we see what we can do is, well, we can create a matrix, B1, B2, Bn. So let's assume that these are written in the standard basis. And we know that if we multiply them by this vector, I'll get x written in standard coordinates. Standard basis. All right. Because that's just how matrix multiplication works. But if I look closely, I see that this piece right here is actually the coordinate vector of x relative to beta. So what this tells me is that I can call, if I call this matrix right here, this is the matrix, and we'll call that matrix P beta, then what I conclude is that P beta times my coordinate vector, my beta coordinate vector, is equal to x in the standard basis. So we call this matrix the change of coordinates matrix. But how? So what I want you to do is observe from our previous example, B1 was equal to 1, 0, and B2 was equal to 1, 2. So that means that our change of basis matrix is just the matrix 1, 0, 1, 2. So the change of basis matrix makes it very easy to go from the beta coordinates to the standard basis coordinates, because we know that PB, P beta times my beta coordinates equals the standard coordinates. How do I go the other way? How do I go from the standard basis coordinates to beta coordinates? How do I go the other direction? I want you to pause the video and think about how I can manipulate this expression to go the other direction. Take my vector in standard coordinates and translate it to beta coordinates. All right, now that you've had a chance to think about it, you multiply both sides by p beta inverse. We see that this piece just becomes the identity. And therefore what we get is that the coordinate vector of B is the inverse of the change of basis matrix times my vector in standard coordinates. So this is beta coordinates, and this is standard coordinates or standard basis coordinates. Okay, whatever. All right, so I want you to find P inverse for what we've been doing before. So go ahead and pause the video and find PB of inverse when PB or P beta is the change of coordinate matrix from before. Okay, now you've had a chance to do that, you should get that P beta inverse should be equal to 1. Here's a 0. Here's a 1/2. And this should be a minus 1/2. All right, that's PB inverse. And what do we notice about it? Well, if I have my PB inverse times my x in standard coordinates, that's this matrix 1, negative 1/2, 0, 1/2. And I take my vector that was in standard coordinates before, that was the vector 1, 6. If I do that, I find that I get, let's see, this is 3, and this is 1 minus 3, so that is minus 2. And this is equal to my vector in beta coordinates, just like I did before. Okay. So one thing we should observe is that P beta is an invertible matrix, just like we have seen before. And so if I take a vector x in beta coordinates and I send it to P to beta inverse in standard coordinates, we see that over here, this is in our, this is in the real numbers to the n, and this is in the vector space V. And so P beta is P beta, since it's invertible, gives us a function here. So this is a map. It's actually a linear transformation. Furthermore, we know that it's 1-to-1 and it's onto. And a linear transformation that's 1-to-1 onto, we call an isomorphism. All right. Okay. So now that we've done some work there, let's switch to some other examples where you can test out what you know about p beta. All right. So let beta equal 1 to t squared t cubed. This is the standard basis for P3. And what I observe is that a typical element P polynomial is equal to a constant plus a constant times t plus a constant times t squared plus a constant times t cubed. And if I write the coordinate vector of my polynomial, it's an element of the real numbers to the fourth power. And so what this tells me is that multiplication by my coordinate matrix, where I take my polynomial p and I multiply it by so I take my matrix PB, my coordinate matrix, I take the inverse, and I multiply it by p to get p in beta coordinates, and I see that this is an isomorphism from P3 to R4. So what it means is that these vector spaces look identical. All right. So I'm going to give you an example for you to work now. So I want you to prove that this set of polynomials is a basis for P2. And furthermore, I want you to find the coordinate vector, well, the beta coordinate vector. So if this is beta right here, this is my basis beta. I want you to find the beta coordinate vector of the polynomial 1 plus 4t plus 7t squared using the coordinate matrix inverted. Okay. And I'll give you one last problem. So you do this first problem and you do another problem that you'll turn in with your notes. And this problem is to find the coordinate vector x beta, where beta is equal to the following set of vectors. And furthermore, our vector x is equal to 8, -9, 6. And so for this problem, you're basically going to solve. This is B1, B2, and B3. You need to solve this equation. All right. Well, that's all I've got for today. If you have any questions, feel free to email me. Otherwise, have a good weekend.